Okay, so this presentation is implementing static vector. How hard could it be? Spoiler alert, surprisingly easy. No, not really. Actually, somewhere between hard to impossible, with maybe easy somewhere in the middle there. I'm not sure, but we'll see. We'll see how hard it could be. So first of all, what is static vector? We're all familiar with vector. It's a class template, accepts a template parameter for the type that you're storing in the vector, and it can store any number of elements and it dynamically allocates them. Static vector is a little different because it accepts a capacity as a compile time argument, and it can only store up to that many elements. And the benefit that gives you is that by making the capacity a template parameter, then you don't have to actually dynamically allocate any memory. All of the memory can be stored in the object itself. So I'm gonna show an example of the memory layout. And the value type I'm using for this example would be something that looks like this. And I chose this particular value type because it actually matches a specific value type that I was working with that kind of drove me to implement static vector to begin with. So this is my real world example as a type that looks just like this as the value type. So up at the top, we have the memory layout of standard vector. Or something like this for various vector implementations. They'll all have a pointer to the data, and then you can have either the size or a pointer to the end, and you can have the capacity or a pointer to the end of the capacity. It functionally works out to be the same, some minor differences in optimizations, but this is basically the general layout of what the vector looks like, this top data structure. The bottom section here in the box is what static vector's data layout would look like. So you can see right away that for this case, it's able to hold between 0 and 4 elements of that 4-byte type that I showed before. So 16 bytes of data total. And you can, some things immediately jump out here. Specifically, it takes up less space on the stack for a small number of elements. There's no memory indirection because the data is stored directly in the object. And those two things are actually very important for performance. When you look at vector, you have that pointer there means that you need to load data from another place in memory. And that's actually one of the slower things that you can do on modern computers is going to dynamic allocated memory, anything that's not in cache. Whereas static vector, by storing the memory directly inline, if you allocate this on the stack, the data is going to be on the stack, and that's a hot data section. It's going to be in cache. The stack is the hottest data section you've got, and in some cases it can even be passed in registers if you're passing it through functions. So this slide right here, I think, is the most important slide for understanding what static vector is. If you can understand what this slide is, you've understood the performance implications of vector, why you would use it, what the pitfalls are, everything. But obviously, this isn't enough to really understand it. So we're going to have to go into some code examples, talk about some benchmark results, things like that. So here is an outline of some of the important parts of the interface of static vector. It looks a lot like vector. I've included basically just the functions that I'm going to be talking about in this presentation today. So for instance, it doesn't include clear, it doesn't include insert or erase, because once you know how to do pushback, popback, things like that, clear, erase, insert, all of those things function similar enough to vector to where you can kind of figure out between the two. So this is kind of I'd say a basic standard vector interface. So going back to the memory layout of just standard vector, one of the interesting things here that stands out is that in this example, the size can be stored in a single byte. This is an important optimization for static vector, because in this example, the entire data structure takes 18 bytes. If we used size t to store the data on a 64-bit system, the size would require 8 bytes, and it would require 24 bytes to store the whole thing. That's a 33% increase in size. And you might think that's 6 bytes. 6 bytes isn't a big deal. Who cares about 6 bytes? But that 6 bytes could be in a data structure that's stored in another container, and you have many of those. Or in my use case that caused me to write static vector, it was stored in another data structure where there were 0 to 6 of them. and then that was stored in another data structure where there were always 2 of them, and then that was copied millions of times a second. So now that 6 bytes turns into hundreds of megabytes per second, and now that's a number that really means something. So the size optimization is kind of the first thing I want to talk about. So we need to look at what's the size of the size. So this is a little bit of metaprogramming. Most of this presentation is going to be pretty light on metaprogramming and more focused on data layout and things like that. So I wanted to get this kind of out of the way at the beginning. But I think it's a pretty straightforward. It uses Boost HANA to be able to use a sort of value-like syntax. This could also be implemented in kind of the more traditional metaprogramming way with class templates and specializations of class templates with a nested type member. But this, in my testing, actually compiled faster than the class template specialization version. Who doesn't like faster compile times? And I think it's also a little easier to read, because you just read through, if the capacity is here, if it fits in an unsigned char, use unsigned char, unsigned short, and so on. So anywhere where we see size type with angle brackets after it, I'm referring to this, and it's basically just the smallest unsigned type that's able to hold 0 to capacity -1 elements. Or 0 to capacity elements, I should say. So now the other part of it is the storage of the data. When I talk about this, one of the first things that people suggest is, hey, what about, instead of doing all this work to write static vector, we just take advantage of what's already in the standard library? What if we use standard vector with a stack allocator? And so that's what this code is, it's doing something kind of like this. I left out some of the details here, but you could write a memory resource, which is an array that you store on the stack, has some bytes in it, and then a stack allocator that stores a reference to that memory resource and allocates from that stack. And this has a few issues. The foremost among them, in my mind, or I guess the first among them, would be that this kind of breaks value semantics. For instance, what happens if someone wants to do this? This is a bug. The reason this is a bug is because stateful allocators are reference types. They reference the memory resource. The memory resource is stored outside of the allocator. So when you return the container from the function, the memory resource, the array of bytes, goes out of scope. All of your data is gone. That's bad news. Now, if you wanted to fix this, your function would now have to accept an allocator or accept a memory resource that you then pass in, and you need to remember to do that everywhere, and it complicates the way the code looks. The fundamental issue here is that vector and static vector are value types, and allocators are reference types. So when you combine the two, you end up with a type that's kind of a mixed value type reference type, and you have to take extra care when you're working with that. Whereas if you just use static vector or vector, you don't have to worry about these types of pitfalls. But there's a second issue. This is the memory layout of a vector with a stateful allocator. So now we have the pointer to the data, the size, and the capacity that we used to have, and we also have the pointer to the memory resource. Now, this is going to perform a whole lot better than just vector would, because the allocation is really fast. You're just incrementing a pointer into your stack allocator. And deallocation is really fast, because you don't have to do anything. But it's still an indirect access, and that can interfere with optimizations. When you're dealing with data members, unless the compiler is able to optimize out the structure entirely, it's not able to optimize out the data members. So when you look at the generated code, you're going to see these data members in there just because they have to be in there. So using a stack allocator will improve your performance over just standard vector, but it doesn't go all the way to static vector. And if you're relying on this size optimization, then it's not helping at all. So in the application I was talking about, after switching from vector to static vector and spending a lot of time optimizing it, the two functions that I'm spending my most time in the application are aligned memcopy and unaligned memcopy. And it's from copying this data. And so if I had a stack allocated vector, I'd have to copy 32 bytes when I only have to copy 18. That's a big loss. So the next suggestion that people often give is, OK, just use an array and have a size to say which elements of the array are active. So does anybody see any issues with this code, trying to use it as static vector? Yes?
You have to construct the objects.
Exactly. This code always constructs capacity objects, and it always destroys capacity objects. So maybe your type isn't default constructible. Then you can't use this at all. Or maybe your type is expensive to default construct. For instance, on some implementations, node-based containers like standard list allocate a Sentinel node. You don't want to pay for 32 allocations if you're only going to have 2 elements in there. That can be expensive. Yes, on some implementations. Specifically, Visual Studio's implementation of standard list does. Lib C++, which is Clang's implementation, does not, and GCC's, I believe, does not. Does not, yes. But there are more types than just the standard library types. There are user-defined types that do who knows what in their default constructor. And we're trying to write a generic type here that can just store things, and you don't want to have to worry about what does the type do when you're storing stuff. So let's move on from this and see if we can come up with something better. You might think, okay, instead of an array of t, make an array of bytes, and then I can construct stuff in here. Does anybody see a bug in this code? This one's a little more subtle. Alignment, exactly. The array of bytes is byte aligned, so that's going to be alignment of 1. Let's say you want to store a static vector of pointers. On my system, that has an alignment of 8. If you violate alignment, that can lead to a whole bunch of issues on your processor. It could mean your code is sometimes slower, could mean it's always slower, could mean it crashes. And just from the C++ standards point of view, it's undefined behavior. And if you have undefined behavior, that means you can't use sanitizers to check for other things. It means you can't run it at compile time, because you can't have compile time undefined behavior. So this isn't quite right. But there's kind of a few things that we can do here. I want to pull this code out, though, into a new type that I'm calling uninitialized array. The purpose of uninitialized array is to just maintain the storage for the data, but not the lifetime of the objects themselves. So this way, we can forget about the size, we can forget about anything else. We can focus on just the thing we're looking at right here, which is the storage. So we go here, we still have the alignment problem, but then we can fix it. There's a type in the standard called align storage. Hey, that's nice. We could also have put align as, align of t there, but we have a ready-made type for us, so let's use it. So this fixes the alignment problem. Anybody see any issues with this code? This one's even more subtle. What's that? Stood launder. No, if I have time, I'll talk stood launder at the end of the presentation, but that is not the issue here. But that is a very good thing to bring up. In some versions of the standard, it would have been an issue, but it is no longer an issue. Yes, constexpr. Data is now reinterpret casting, and reinterpret cast is one of the things you cannot do at compile time. In C++ 20, we added constexpr support to vector, mostly. You can create a vector in a constexpr function. The one limitation is that you cannot create a constexpr vector variable. And the reason is that when you allocate memory at compile time, you have to deallocate it at compile time. Static vector doesn't allocate memory. So you would think, hey, if the only thing holding vector back from being fully constexpr is the memory allocation stuff, and we take that away, we should have a constexpr static vector, right? And it'd be kind of disappointing if we don't have that. So now we're kind of stuck here, because anything that uses a byte-based solution, we can't use at compile time because it requires a reinterpret cast. And anything that uses just a t-based solution, we can't use for a large set of types. So this doesn't work either. How about we combine the two? We can make at least a static vector that's constexpr with certain sets of types. And that gets us a little closer to where we want to be. So now we have to have a little bit more metaprogramming, but not a lot, where we have this is sufficiently trivial property, where we're saying if the type is trivially default constructible and trivially destructible, then we can create as many of those things as we want, and it doesn't matter, because default constructing them and destructing them does nothing. That's what trivial means. It's a no-op in this case. So if the type is trivial, we create an array of the type. Otherwise, we have bytes. And then we can use it at compile time for any of these sufficiently trivial types. So now we can have a static vector of int and use it at compile time, and everything's good. But if we wanted a static vector of, say, strings, we're out of luck right now. So is there anything smarter we can do here? Yeah, not so much. It turns out that it is possible to remove the trivially destructible requirement by getting really clever with unions. But the advantages of that are basically nothing, because I don't know of a single type that's trivially default constructible but not trivially destructible. That'd be a really weird type. It's saying, I have to do something when I'm destroyed, but the constructed state can be whatever. Like that doesn't make any sense. So the usage of it is limited, and Visual Studio doesn't implement that part of the standard yet. GCC does implement that part of the standard with bugs, and Clang does implement that part of the standard with bugs. So in practice, you actually couldn't even take advantage of that yet. So as of right now, I believe this is the most constexpr data storage representation you can have. And that's kind of sad. But toward the end of the talk, if we have time, I'll go through a few things that we could potentially propose to improve the situation and let us have a static vector of anything at compile time, as long as that T is compile time capable. Oh, and by the way, if anyone has any questions, like raise your hand, interrupt me right away. Like you don't have to hold it or anything. Yes, Ben.
Why do you have no unique address on the member variable?
Okay, the question was, why do I have no unique address on the member variable? The reason there is that you could end up with a static vector of capacity 0. If you have some sort of computation of exactly how many elements you need, it ends up with 0. It'd be really nice for that to not take up any space. And no unique address allows static vector to be an empty type when capacity is 0. Yes?
Trivially default constructible guarantees that it doesn't have any side effects as well?
The question was, does trivially default constructible guarantee it doesn't have any side effects? And the answer is yes. It is side effect free because there is no user-defined code that is run when you default construct it. So that's what ints do, it's what pointers do, it's what all the built-in types do. Any other questions? I thought I saw one. Yes?
And this one is a little complicated.
Okay.
To be able to do the pointer arithmetic, doesn't it need to be an array object like behind the scenes?
Excellent question. The question was, to be able to do the pointer arithmetic, doesn't it need to be an array object? And the answer is yes. Now, in C++20, well, I should back up a little bit. Prior to C++20, it was not possible to implement standard vector. All vector implementations, if they were written in C++, had undefined behavior. In C++20, we added a whole bunch of things to make it work. And one of the things we added was a concept called implicit lifetime types, which basically means that there are certain operations you can do, such as allocating memory or constructing an array of bytes, which is what this does, an array of bytes. They implicitly create objects of implicit lifetime type. And arrays are implicit lifetime types, which means that by creating this array of bytes, if we need an array to be there, an array was always there. Now, the objects in the array, their lifetime haven't begun unless they are also implicit lifetime types. I'm planning on giving a lightning talk on exactly this subject sometime this week. So if you're interested, come to the lightning talks. I think that's about as much detail as I can get into for this, but just know that in C++20, the array object is there, the pointer arithmetic is well defined. Any other questions? Okay. So now let's go into the member functions. What do we have to do to actually implement all of the operations now that we've kind of figured out what we want the data structure to look like? So first one, popback. Popback is simple. We just make sure that it's not empty. It's a precondition, and destroy the last element and reduce the size. This is about as simple as you can get. And yeah, so destroy at is a function that was added in, I want to say C++17. It might have been 20. I can't remember. One of the two. 17? Okay. Yeah, it was added in 17. It's just, I think, a more convenient way to call the member destructor syntax because it'll work with any type. Certain types, if you say like dot, tilde, t, manual call destructor doesn't work. So just destroy at consistently works. So pop back, really easy. So pushback, that ought to be easy too, right? That's just the opposite of this, right? There's not gonna be any problems there. And that's almost true. So here we use construct at, and here constructed is actually necessary because the alternative is placement new. And placement new accepts a void star. And void stars are, like, to be able to use them, it's essentially reinterpret cast. Placement new is not usable at compile time. So if we want it to be constexpr friendly, we have to say construct that, which is fine. It's the exact same thing. And we increment the size. But now there's this one little wrinkle here. We need to check that it's not full. Now I know what you're thinking. You're thinking, check not full, that's a horrible name. That's a negative name. We need to have a positive name. So not full, what's a word for not full? Hungry. Okay, there we go. Excellent name for our function. Check that the vector's still hungry. Okay, so we have a few things we can do here. We can say, okay, if the size is equal to the capacity, throw bad alloc. This is what vector does, kind of. When we look at vector, if we call pushback, it allocates new memory. And if it can't allocate new memory, it throws bad alloc. Static vector, by definition, can't allocate new memory. So maybe it should throw bad alloc. But that's kind of weird. We have a type, and we said, this type never allocates memory. And then you do an operation on it, and it says, oh, that allocation was bad. Like, I don't know about that. That seems kind of iffy. So what else could we do? What other options do we have? And also, like, does it make sense to do other options? Because remember, the reason that we considered this is because this is what vector does. And we want static vector and vector to have basically the same interface. It makes sense that they'd have the same interface because they're basically the same type, just one of them binds the capacity at compile time and makes it fixed. However, there's an important difference here. With vector, it is not possible to check in advance whether the allocation would succeed, whether it is capable of getting new capacity. And there are two reasons for that. In a multi-threaded case, there's a time of check, time of use issue, which is before you allocate memory, if you said, oh, hey, vector, are you at your capacity? Yes, okay. Is there free memory for you to allocate? I mean, first of all, you have to know how much memory vector is going to allocate, and that's not specified. But even if you could know that, you could say, oh, is there free memory? And the system says, oh, yeah, there's free memory. And then you allocate, and some other thread came in and allocated memory, and it says, oh, now there's not free memory. So you couldn't check there. But even in like some sort of idyllic, single-threaded case, you still couldn't check. And the reason is that the amount of work that you have to do in a memory allocator to check, is there free memory, is pretty close to the amount of work you have to do to say, give me memory. And it would be really sad if we required all users of vector to pay a memory allocation cost before every pushback when capacity is full twice. So that's why vector says you can always call pushback, and if there's no memory, we'll report it using an exception. Now with static vector, that's not the case. For static vector, you can always check, is it equal to the capacity? And you always know what the right answer is. And that's a cheap check. You're just checking a member variable against a constant. So here's another implementation of check hungry. Assert the size is less than capacity. It's basically saying it is undefined behavior to call pushback when the static vector is full. This is the direction that was chosen by the static vector proposal for the C++ standard library, based on basically this reasoning. And so some people might not like this because undefined behavior is kind of frustrating, right? Like it's a difference in the API between vector and static vector. It's one thing that kind of makes it to where you can't just do a drop-in replacement. But the good news is that it's possible to layer an operation on top of this efficiently. If you have a pushback that has behavior when it's full as undefined, I can write my own checked pushback that accepts a static vector and adds something to it. And if it would overflow, throw an exception. Like that's kind of the layering approach that we typically use in the standard library. So this is kind of the direction that I would take. And so now that we have this as our implementation, it makes sense to just inline it into pushback, express the precondition right there. Now, the issue here is that the decision that we make in one part of the code kind of ripples out to the rest of the code. So we say, okay, pushback, undefined behavior if you exceed the capacity. But pushback is easy. Pushback is one element. What if we want to add a bunch of elements? Range constructor. Okay, so now this gets trickier. Because that range, that iterator pair that we're passing in, what if it's forward iterators? Now it's expensive to check the size. The very thing we were trying to avoid before is doing work twice. If the user has to check the size first, and they just have two forward iterators, they have to iterate over the whole range to check the size, to know whether it would fit, to know what to do. And that's not even the worst case. It could be input iterators, which means that it is not possible to go over it twice. Consider the case of an iterator that reads from standard in. After you read from the first one in advance, you're waiting for the user to type in input again. You can't go back and look at what they typed before unless you store it somewhere. Where are you storing it? You're trying to store it in static vector. That's the whole reason you're using this. So there's kind of that issue there. So that makes things a little tricky. Now, there are, fortunately, some things we can do. Ranges somewhat comes to the rescue. In C++20, there is an addition to the standard library, standard ranges take, I think, or views take, where you can specify, take the first n elements from the range. So if the behavior you want is from this range, take up to the capacity of the vector and then drop the rest, great. That's built into the standard library. You can just do a range adapter and you're good to go. But if the behavior you want is throw an exception, that doesn't exist. There is no, iterate through with a counted iterator and throw if you exceed it. So you have to do the work of writing a range, your own custom range adapter for that, which isn't quite easy yet, I would say. I think there's probably a presentation here this year on ranges, I'm assuming. There usually is. But yeah, it's at least possible to layer that behavior on. But I think this is kind of a hole in the standard library right now, is the difficulty of writing range adapters. Yes?
There is a proposal that, forgive me, I forget, I think it's been forwarded to LWG now. So
okay.
For assisting people that want to write the range adapter.
Excellent. And is that targeted at C++23?
It is.
Okay, so there's a proposal for C++23 to make it easier to write range adapters.
I'll talk about it on Friday.
Oh, and Jeff is going to be talking about it on Friday. So if you're interested, you know where to go. But yeah, so once we have that, like we're moving in a direction to make it easier to layer this behavior on top to check that the range is the right size. So that is kind of it's a trickier case for the range constructor, the range insert function, the range assign function. But it's at least possible to layer on without losing performance. And that's the reason that you use static vector, is for more performance over vector. Yes, Jeff?
Could you not also just use sized range and just say input is just going to be excluded?
Okay. So Jeff's suggestion or question, comment, whatever, was static vector could constrain its parameters to accept a sized range instead. And that would be another approach of basically saying, hey, user, if you're going to use an input range or a forward range, that's pretty risky. You might want to do some sort of range adapter that'll do the size in there or something. That is one approach. I haven't thought about that too much. I'd have to think about it more. Arthur.
That strikes me as a really bad idea.
Okay.
So I don't think a take view is a size range to begin with. So that's like customizing thing a user would try to do to work around this. And I may be stealing the thunder of the next slide, but what about back insert?
Okay. That is not the thunder of the next slide, actually. So the question was about, well, first, disagreement over restricting the types, specifically because the take view is a maximum size, not an actual size. So even if you said, take the first 5 elements, that doesn't become a sized range because it could be less than 5. But then the follow-up question was, what about back inserter? And for those of you unfamiliar, back inserter takes a container and turns it into, it creates an iterator for it where dereferencing and assigning to the iterator calls pushback on the container, which kind of brings us back to the previous slide about what you do with pushback. But yeah, so kind of same issue here, but now applying to pushback there. So like I said, all of these things end up being connected, even when they seem like independent things, which is why it's important to have a consistent design of the whole thing before you really commit to one thing. The next slide actually is about this function, the uninitialized copy no overlap. What is that? So This looks complicated, and it kind of is. But basically, this function is so in the C++ standard, there are algorithms that begin with uninitialized underscore. And what those do is they accept a range, a source range, and a destination range. And the destination range is assumed to not have any objects in them, so that the algorithm will construct rather than assign. So this is an uninitialized copy, so it's copying from a source range into an empty output range. And the no overlap is specifically saying these ranges do not overlap, which means that memcopy is safe to use. That is an important optimization. But memcopy is not usable at compile time. So that's why we have first, is it memcopyable, which is basically just saying, is the range input iterator input sentinel a contiguous range? And is output iterator pointing to a contiguous range, basically pointers? And are the types of the iterators the same? So this is just a custom trait. So if that's true, if it is theoretically possible to memcopy these, if the types would work out, then if it's not constant evaluated, use memcopy. Otherwise, fall back on initialized copy in either case. Now there are two kind of interesting things here. I'm going to start with the boring and more subtle one first, which is uninitialized copy is not std : uninitialized copy. And the reason is that we didn't make the uninitialized algorithms constexpr. They are specified to use placement new, which is not constexpr. They could be respecified to use construct at and become constexpr, but we haven't done that yet. So the good news is that the implementation of these functions is pretty trivial. It's just a for loop. So I'm not going to show those on the slide. Yes?
Okay, this might be a basic question, but it might have something to do with just the definition of constexpr. But there were a couple of examples where you showed that you checked to see if something were constexpr, and if so, you did the constexpr thing.
Mm-hmm.
And if not, you defaulted just like calling reinterpret cast, or in this case, calling a non-constexpr function. In that case, what does the entire signature of the function change when it's compiled in that instance? Like, does the whole function become non-constexpr? Like, if you have to default to the reinterpret cast?
Okay, so your question is basically, in the body of the function, sometimes I use this is constant evaluated. What effect does that have on the function at compile time versus runtime? Would that be a good summary?
Like when you take the branch,
yes.
It's not trivially constructible or destructible, and so therefore it's not constexprable.
Yes.
What happens?
Okay.
Take the other branch.
Yes. So std is constant evaluated. If this function is used in a situation that requires a constant expression, is true. So for instance, if you use it as an array bound, if you use it as an argument to static assert, a template parameter, anything like that, this is a constant expression. And for a function to be a constant expression, the body of the function must be visible to the compiler. So when it is a constant expression, it sees all of this, it substitutes in the true, and it says, okay, if true, do this, and it never takes the else branch, so the compile time interpreter doesn't really have to look at that other than just to make sure it type checks. For the runtime case, it sees if false, some code, else this. And then the optimizer says, oh, if false, I know what to do with that. I just throw that out. And so then the compiled function turns out to be just the else branch. So basically at compile time, it only looks in the path that it takes, and then at runtime, it optimizes out the path that it doesn't take. Does that answer your question?
I think so, yeah.
Okay.
I might ask a follow-up.
Okay. Yes?
Hopefully easier question. So you say uninitialized copy no overlap, but then you call uninitialized copy. Does that mean that if they do overlap, it's just undefined behavior, you don't care, or what am I missing?
Yeah, so the question was about how uninitialized copy no overlap delegates to uninitialized copy. Uninitialized copy no overlap has a precondition that the input range and the output range have no overlap whatsoever.
Yeah.
Whereas uninitialized copy says that they can overlap in one direction. So it's calling a function with fewer preconditions.
So it's like a wider contract.
Yes.
Got it.
Okay. So the other interesting thing here is this call to CPP memcopy instead of memcopy. And the reason for that is that if we want to have an efficient static vector, we have to write our own memcopy. And the reason for that is that memcopy accepts a pointer, and a size. And both pointer arguments are annotated saying they cannot be null. You cannot pass null pointers into memcopy even when the size is 0. And this is inherited from C. The C standard library says that. So why does the C standard library say that? Well, in C, different from C++, null pointer plus 0 is undefined behavior. In C++, that's allowed. In C, it's not allowed. So there are certain implementations of memcopy that would just break on null pointer arguments because you can't even add 0 to them. And there are also some people who like the optimization benefits from this, because by annotating memcopy with non-null, you know going forward and backward in time in your program that any pointers passed in are not null pointers. So this is useful optimizing information. But it means that in our code here, null pointer and null pointer is a perfectly valid range. A default constructed vector is probably going to be null pointer and null pointer, at least on some implementations, because you don't want to have to allocate memory for nothing. So null pointer is a perfectly good range. So to call this code, we would need to check, okay, if the size isn't 0, call memcopy. Just a simple branch. Seems innocent. But it turns out it's not. It's actually a huge performance loss for some workloads. When I was writing this and benchmarking it, I have some example code that compiles down to one instruction as I've written it. And if I call the standard memcopy and check the size not equal to 0, it's about 180 instructions. And that's just because having that branch in there made the code a little larger, which prevented inlining something, which prevented other optimizations, and then instead of just being return a constant, it's a whole bunch of stuff. That's not good. So we have to write our own memcopy. That's a little beyond the scope of this presentation. The good news, maybe, I don't know, is that Clang has a built-in called built-in memcopy. And it's undocumented exactly what it requires, but it accepts null pointers under address sanitizer and undefined behavior sanitizer.
That is in fact a great thing to depend upon.
Yes. But yeah, so that's not, GCC also has the built-in, and it doesn't accept null pointers. So it's like, even then, like, you'd still have to do something. So like the right fix here would be go back to C and say, hey C, here's important performance data showing that you're actually losing performance by restricting this from being null pointer. So if we make this change, then the upstream changes can start to fix that. So that's that. Yes?
On the previous slide, weren't you calling memcopy in the constexpr case when it was constant evaluated?
It's if not constant evaluated, call memcopy. There's a little.
That'd be nice for old people, whole thing. I didn't know.
Not. Okay. Yeah, no problem. Okay, move constructor. The move constructor for static vector is a lot more interesting than the move constructor for regular vector. Because for regular vector, it's just a pointer and a size and a capacity, and you can just copy those over and then set the old ones to 0 and you're done. And in fact, the standard requires that a move from vector is empty. It's rare among types in the standard that we actually say what the move from state is. For static vector, though, it's a little more nuanced. The static vector standardization proposal proposes the same behavior for static vector as for vector, which is to guarantee that the move from state is 0. But I'm actually proposing a different behavior as the correct behavior for static vector. So this relies on an addition in C++20 called conditionally trivial special member functions. Basically saying, if the type we're storing in static vector is trivially move constructible, then the move constructor for static vector should also be trivial. Because trivial operations are really nice for the compiler. It can just mem copy stuff around. Other optimizations or other code might depend on that, taking the fast path for trivial things, like we saw earlier in our own code. Now, if that doesn't work, like if it's not trivial, then we have some choices to make. And so now for the code here I'm showing, I'm using an operation called relocation. Now there's a whole lot of different things that relocation could mean. Yes?
Does trivially move constructible implies trivially destructible?
Does trivially move constructible imply trivially destructible? No, it does not.
Does that make it broken?
No, because this makes this move constructor trivial. The destructor of static vector would look something similar, of saying if the type is trivially destructible, make it trivially destructible. Otherwise, member-wise destroy each element.
Okay, so we destroy more copies.
But yeah, so relocation can mean a few different things. And all of that is wrapped up in this uninitialized relocate no overlap function. That can mean whatever you're able to get relocation to mean, whatever you want it to mean in your code base. There's a few things here. So for instance, one of them is trivial relocation. This is a really important optimization. Arthur gave a presentation on this, I think 2 years ago, right here at CppCon, or C++ Now, one of the two. You can search online for Arthur O'Dwyer, trivially relocatable, and his blog will come up in his videos, and he kind of goes through that. So that's one aspect of it, and that's really important for optimization. Most types are trivially relocatable. But there are also types which are not trivially relocatable, but can still benefit from an optimization similar to relocation. For those of you who aren't familiar, relocation is basically saying that we're instead of just doing a move construction, we're combining the move and the destructor into a single operation. For a trivial relocation, that's memcopy. That is the single operation. But it turns out that there's optimization benefits for relocation even when it's not trivial. Because when you do an uninitialized move, what you're doing in memory is you're saying, okay, I'm starting at the beginning of the source and the beginning of the destination and doing a move construction from the source to the destination and moving forward in memory on both of them. Then, at some later point in time, hopefully soon, you're going to destroy other. Because R values typically mean it'll be destroyed sometime soon. Hopefully reasonably close. And when that happens, you start at the beginning of the source, and you go through, and you destroy each element in turn. Which means that you're visiting the source range twice, possibly far apart in time, with some amount of intervening code that makes it harder for the optimizer to see what's going on. Relocation says, okay, let's package that up into one thing, move construct, and then destroy. So we visit each element in the source once, both in terms of closest together, but also in terms of iteration. And this has very large performance benefits for certain source ranges, and also makes it a lot easier for the optimizer to see exactly what's going on and optimize things away down to nothing. So uninitialized relocate, no overlap, handles that behavior. Now for the libraries that I work on, relocation is defined as being no except because it is a destructive operation. Just like destructors in general should not throw, a relocation is a destruction of the source object, so it should not throw. So it's basically a check of saying, in my library it says, hey, if the default implementation is move constructor and destroy, and if the move constructor isn't no except, it says, hey, you need to either opt into a new relocation or you can't use it, and we have to fall back to this other thing. So relocatable will be false. Yes, Arthur.
I just wanted to add one more thing about relocation, just to emphasize what you're saying, that if you're thinking about relocating a unique footer from point A to point B, relocating the unique footer is branchless, but destroying a unique footer has a branch.
Yes.
You have to check whether it's null and do one thing or the other.
Yes, for those of you who couldn't hear that, Arthur gave an example of unique pointer being relocated. Relocating a unique pointer is branchless. All you have to do is memcopy the bytes. But if you do a move and a destroy, there's a branch built in there because you have, there's, possibly a few branches really to handle certain cases. No, move construction, just one branch. I was thinking move assignment. But yeah, basically you have to check, is there a null pointer stored in it? If not, then call delete, otherwise do nothing. So yeah, relocation is a big win. We want to make sure we support it. Yes. Sorry, hold on. Yes.
It looks like there's two new constructors on this slide. The first one doesn't say constexpr, so can you just comment on the constexperness of the first one?
Yes. So the comment was that there are two move constructors defined here. The first move constructor doesn't have the constexpr keyword on it. The second one does. When you have a defaulted function, constexpr is deduced. So if the underlying operation would be constexpr, this is constexpr. In this case, we know that it's constexpr because it's trivial. Trivial operation, a trivial move is going to be a constexpr move. That's fine. So I could have put constexpr there and it would have meant exactly the same thing.
So if T is actually trivially move constructible, why are then these not two different definitions of the same function?
Yes, so the question was, if T is trivially move constructible, why are these not two definitions of the same function? So that was what I mentioned, the conditionally trivial special member functions. The fact that this move constructor, the trivial one, has a requires clause on it. Basically, overload resolution is done between these two functions, and requires clauses are considered a better match than non-requires clauses when the signatures are otherwise the same match. Yeah, that's since we've had requires clauses. It's a constrained definition is a better match than an unconstrained definition. And I believe you had a question? Yeah, so STD exchange, it could have been written as two things of just saying m_size equals other.m_size, other.m_size equals 0.
Yeah, of course, but why do you need to set it to 0?
Yes, excellent question. So why do we need to set the size to 0 for the other? The reason is that relocate is a destructive operation. The other static vector, after it's been relocated from, has no more elements in it. They've been destroyed. But the size still says, oh, hey, there's elements here. So we need to set that size back to 0, so when the destructor of the static vector runs, it doesn't destroy any elements. Okay, any other questions? Yes?
So, are we still assuming that these are going to be trivial? Because if it's relocatable, it's going to be no except, but if it's not, you're going to come down here and do your uninitialized move. Are you expecting that an exception could be thrown in there? And what will happen to your data in that case?
Yes, great question. So it was about the no except specification here. So this function says it is no except if it's relocatable only. And the reason is that you can define a relocate operation as a move construction and a destroy. But because there's a destruction in there, it can be dangerous to do that if the move throws an exception. So in the library that I use based on this, if the move throws, you don't get a relocate built in for you, which means that you already know if it's not relocatable that the move is a throwing move. Because if the move were a non-throwing move, you would get a relocation operation that you can use in this algorithm. Does that make sense? Yes?
I think what Jody is saying is, based on how he loves no except specifications, if you have a type T that is not trivially move constructible and not relocatable, but yes, no throw move constructible, then your no except is overly conservative.
Yes, so the concern was that if you have a trivially move constructible, or a non-trivially move constructible, non-relocatable type, but is no throw move constructible, that this no except specification will be wrong. But we don't have to worry about that, because if it is no throw move constructible, it can be relocated using that synthesized move destroy operation. So it's not trivially relocatable, but it can be relocatable. Any other questions? Yes?
So, in the case that the move construction can throw, and in fact does throw,
Yes.
after some elements have been moved, in this case, since static vector's destruction is based on m_size, and that's responsible for destructing the ones that may have been successfully moved, if it throws before we update m_size, is that going to interfere with that?
Yes, so the concern was in this else branch, what happens if move throws an exception? Which is a great question. So in C++, the sort of minimum thing required from a move from type is that you can still run a destructor on it. And then hopefully you can also assign to it. And then for standard library types, you can call any functions without preconditions. And maybe for your types you can, maybe for types you can't. But you minimally have to be able to destroy the type. A move from object is still an object. It's just in some unspecified state. So Yes. So the implementation of uninitialized move needs to ensure that the destination objects have all been destroyed in the case of an exception. And here, uninitialized move is not std uninitialized move, again, just for constexpr reasons. But std uninitialized move does handle that case. Any other questions? OK. Swap. So here's another example of where static vector and vector are not drop-in replacements. Swap on a static vector, or on a vector, basically just swaps the pointer, swaps the sizes, swaps the capacities. Really simple, no except, constant time, references and iterators are not invalidated. For a static vector, that's not the case, and it can't be the case, because the objects are stored in the static vector itself. So to swap static vectors, you have to swap all of the elements. And actually, this slide has a bug. I should also swap the sizes. So I'll have to fix that. But basically, the difference in behavioral guarantees between static vector and vector here are you don't get reference stability and you don't get iterator stability. And what that means is that after a swap, if you have a reference to an element in the vector, that reference is no longer valid. You have to go back to the other vector and get a reference to it if you want to keep it. Same with iterators. So there's there is this API difference that's unavoidable just by the very nature of how static vector stores its elements. And I think, in fact, that this would make static vector no longer be considered a container or a sequence container in the C++ standard because it doesn't have a constant time swap. Yes?
Yeah, I was going to say that, to me, that is the big thing here, that the reference stability and the iterator stability is unfortunate, but the fact that swap is no longer constant time
Yes.
is a huge thing. By the way, std array has the same problems.
Yes.
It has the same behavior.
Yes. That static vector, along with std array, don't meet the full sequence container requirements in C++ because they have linear time swaps. That is an important foundation of the C++ standard library is guaranteeing algorithmic complexity for various operations and calling out any times where you don't meet that. So to review, improvements that we could make to the standard that would make static vector better, easier to implement, more featureful, any of those things. Memcopy, we'd have to fix the C standard for that. That's kind of tricky, but I think I'm hoping that they would be amenable to the changes because it can be a really big performance win, allowing memcopy of a null pointer if the size is 0. Making the uninitialized algorithms constexpr, that was probably just an oversight, ran out of time, no one proposed it, that sort of thing. Like there's no technical reason why it isn't there other than that we didn't do it. Adding relocation to the standard, specifically trivial relocatability is something that I think we need standard support for, or at a minimum, compiler attribute support for to be widely useful in a way that doesn't cause people to write bugs. And then the final thing is making uninitialized array actually possible. So if you'll remember, we kind of had this hybrid implementation where we said, oh yeah, if it's trivial enough, then store an array of t, otherwise store an array of bytes. And that's kind of disappointing because it means that a static vector of int can be used at compile time, but a static vector of a static vector of int can't because it's not trivially default constructible because you have to set the size to 0. Like that's really frustrating. And it's really disappointing that we have vector, which is usable at compile time. And then we have static vector, which takes away the one thing that was hard to do at compile time, and then we can't use it at compile time. So, how do we fix this? There's a few approaches that we can take, a few ways that we can go here. One of them would be uninitialized array is just added to the standard. It's a magic library type that the compiler and the standard library have to work together to somehow do. There's already an attribute in Clang called Clang no destroy that says, don't destroy elements of this in the destructor. Don't if it would implicitly be destroyed, don't actually run the destructors. That was intended for static destruction of things that only allocate memory. But that could be pressed into service here for an implementation-defined thing, and then we just have to fix the construction half of it. So that would be one approach. I don't really favor that approach. I think it would have a hard time getting through the standards committee because that's a pretty big magic library type thing. The closest analog we have is initializer list, which people don't really like. Another option we could take is trying to standardize some of these building blocks that we would need. Some sort of way of just saying, don't initialize this variable. That's been proposed a few times. Some sort of like no init tag on a variable declaration. Other languages, for instance, Rust has solved this problem with, I think it's called uninit t, where you can, you can write this in C++. You can write an uninit type, which is basically just a union that stores that type. The issue is that you can't have an array of uninitialized and treat it as an array of t. The strict aliasing rule prevents you there. So we could have some sort of relaxation of if you have an array of a union that just has a t, you can treat that as an array of t or something like that. There's a lot of different directions, and none of them are super satisfying, which is why I haven't written a paper for it yet. But I think this is an important problem to solve. So if anyone has any ideas, I'm open to hear. Yes, Timur.
Just to make sure I understand what an uninitialized array would do.
Yes.
So it would be something like std array, for example, and you say it has like 100 elements.
Mm-hmm.
But then when you construct it, it wouldn't construct these elements. There would be notionally there, but they wouldn't actually, the size would be 100, but there would not be elements in there. And then if you do write elements in there, you just write them over these non-existing objects, and from then on, those elements behave like normal elements. Did I get that right?
Close, yes. So the question was like, what would this uninitialized array be? And kind of what I'm imagining is, something kind of like standard array, where you give it a type and a size, and it provides storage for that many elements. So the default constructor wouldn't initialize any elements, and the destructor wouldn't destroy any elements. It would be the user's responsibility to use that as storage to construct and destroy as they see fit. So it would be trivially default constructible, trivially destructible, but it would be providing typed storage, so you could use it at compile time.
Basically like aligned storage, except you can actually get elements in and out.
Yes, it's typed aligned storage. Yes, exactly.
Okay, cool.
Arthur.
Just this idea that inside std variant, there's another useful primitive, which I call recursive union.
Mm-hmm.
Same idea. It's like storage for the union of t and u and a v and however many things you have in variant, but the lifetime stuff is all up to the end user. It's the same idea.
Yes. So the comment was that the implementation of variant uses something similar of a recursive union or recursive variant storage or whatever you want to call it. And yeah, so that exists, and it's kind of unfortunate the compile time implications of having to have one variant at each level. One of the things that I actually considered to implement this was something kind of similar to that, where it would be like, okay, what if we had a variant of an array of size 1 and an array of size 2 and an array of size 3, all the way up to the capacity. But it turns out there's no way to convert from an array of size 3 to an array of size 4 without losing all of the elements you had there. And there's no way to start out with the big array without actually initializing all the elements in it. So that was a dead-end approach as well. Yes, Timur.
In order to, like this uninitialized array thing, status quo is that it's unimplementable, right? So you have to actually do core language changes in order to do that first, right?
Yes.
Like, probably on top of some of this like object lifetime stuff that Richard did, but that's not quite enough, is it?
Yeah, so this requires core language changes unless we just say it's a magic library type that just does it, which I don't think we're going to get. I think we need the core language changes, and I think that's a better design. And by the way, this is the end of my slides, so if you have any other questions, raise your hand now. Yes.
And a question on the swap. Right.
Yes.
Doesn't the swap ranges need to know how long RHS is in order to function properly? If you have two vectors of different sizes.
Yes, so this has multiple bugs. That is a good point. So the story behind the swap was I actually had a different swap implementation that was a bit more generic and handled some other things that wasn't needed for static vector. I'm like, oh, I'm just going to pull that stuff out and just have what I need on the slide, and didn't actually bug test this slide. The other slides were actual code from my implementation. This one was slideware that I now know not to do.
Yes, so Ryan earlier was talking about wanting to have at concept for time the ability to at least be able to cast between a void star or a data member and an actual type, just going back and forth between those. If we had something similar to that and a constexpr placement new operator, could you do what you want to do?
Well, I mean, so we do have a constexpr placement new operator mostly in the form of standard construct at. The only thing that it's missing is the temporary elision or the guaranteed copy elision or whatever you want to call it. And you can kind of fake that with some things. But the first part of your question, I don't fully understand.
Well, the problem is you have the data, there's no conversion between pointer types at file types.
Yeah. Yeah, so that, I mean, yeah, we would either need, yeah, so another approach would be some sort of reinterpret cast or a limited reinterpret cast that's usable at compile time. That's basically what that amounts to, is a way to convert between this type and that type at compile time. Or a way to have typed storage at compile time. Am I out of time now?
Yeah, the session is over.
Okay. Okay. Yeah, so there's going to be a Q&A follow-up tomorrow at lunch. I think I have to let you all go now. You've all been great. Thank you for coming.